In this video, we're going to use the characteristic equation of A to find eigenvalues and eigenvectors. The characteristic equation is given by the determinant of lambda times the identity matrix minus matrix A set equal to 0. It is a polynomial of degree n where the variable is lambda. Let's use the characteristic equation to find the eigenvalues and eigenvectors of matrix A, where matrix A is equal to 3, 2, 4, 1, and is a 2 by 2 matrix. Since we don't yet know the specific values of lambda, we're going to write the characteristic equation of A as follows. The determinant of lambda times the identity matrix minus A is equal to the determinant, and here's our identity matrix. We're just using the symbol lambda for now to represent our unknowns, minus our given matrix, okay, so from here we subtract our two matrices, so we get lambda minus 3 for the first entry, 0 minus 2 for the second, then we have 0 minus 4, and lambda minus 1. We wish to take the determinant of this. It's still a 2 by 2 matrix, and just to simplify a little, what we really have here is lambda minus 3, negative 2, negative 4, and lambda minus 1. So here, we're finding the determinant, and we're going to need to use the FOIL method for the first two terms. So we have lambda minus 3 times lambda minus 1 minus negative 2 times negative 4. So we FOIL. We have lambda squared minus 4 lambda plus 3, and then minus 8. This simplifies to lambda squared minus 4 times lambda minus 5. We factor the trinomial, so we have lambda minus 5 times lambda plus 1, set it equal to 0. And then using the zero product property, we set each factor equal to 0 and end up with lambda equals 5 and lambda equals negative 1. Now ultimately what we're looking for is the solutions to the homogeneous system based on eigenvectors that correspond to the eigenvalues lambda equals 5 and lambda equals negative 1. Let's start a new. And we'll begin by finding the coefficient matrix for when lambda is equal to 5. Using the characteristic equation without the determinant piece gives us 5 times the identity matrix minus matrix A. And so that gives us here 5 times 0, 5 and 0 for the second entry, 0 and 5 for the third and fourth entries, minus our original matrix A, which is 3, 2, 4, 1. Subtracting these matrices gives us 2, negative 2, negative 4, and 4. Next, we need to write this in reduced row echelon form, which, since this is a longer equation, I would just use a graphing calculator to find out what this is. And if you're not sure how to do it, take a look at one of the previous videos in this unit that deals with reduced row echelon form. For now, we'll assume that everyone is familiar with how to do this. So we're taking the reduced row echelon form of A, or rather 5 times I minus A. And that gives us entries 2, negative 2, negative 4, and 4 in our 2 by 2 matrix. This is the coefficient matrix. So we take our reduced row echelon form of the 2 by 2 matrix, found by taking 5 times I minus A. This result is what we call our coefficient matrix. And we find that our reduced row echelon form is 1, negative 1, 0, and 0. It follows that the solutions of the homogeneous system that have this coefficient matrix are all of the form T, T, where we have a 2 by 1 matrix, and T is an element of the reals. Factoring out the T, we can conclude, therefore, that the eigenvalues corresponding to lambda equals 5 are non-zero scalar multiples of the 2 by 1 matrix 1, 1. Now let's find the eigenvectors that correspond to the eigenvalue negative 1. So when lambda equals negative 1, we have negative I minus A equals the identity matrix multiplied by the scalar negative 1 minus our original matrix A which equals negative 4, negative 2, negative 4, and negative 2. Next, we want to take the reduced row echelon form of this matrix, and we end up with 1, 1/2, 0, 0. Therefore, the solutions of the homogeneous system when lambda equals negative 1 are all of the form 1/2 t and negative t, where t is an element of the real numbers. So the eigenvectors that correspond to this are the non-zero scalar multiples of 1/2 and -1. So this concludes our example. I hope you found it helpful, and we'll see you next time.